Hello everyone and welcome back to my another video. So recently I started checking out the object detection stuff that I did quite a long time ago, and recently I needed this in my work, so I thought that it would be nice to create some kind of useful tutorial related to my machine learning training utilities, because I decided to integrate this object detection trainer into MLTU. So this should be really useful for you and also for me. I will answer you why. For example, I decided to use an Ultralytics Object Detection that is running right now while I'm recording, and you might ask how it works. Well, basically, I created a second virtual camera that I'm streaming while recording. This is why it's a little slower, but it doesn't matter, it works for me. And you can see how it records. And yeah, that's it. So basically, I decided to create this tutorial, and this tutorial will be only to demonstrate how easy it is to use the train model with, for example, with Ultralytics. But the idea here is that I'll train the model with my MLTU package, because there is a huge disadvantage with Ultralytics. They are doing everything just perfectly. They're all working with the models and etc. But when we come with a flexibility in training, for example, using custom data set, using custom augmentations, custom transformers, or whatever, it starts to get really hard to do such thing. So I decided that I will use the Ultralytics for the model stuff, and I'll use my own MLTU package for training. And you'll see how easy it is to use it. For example, right now I'm running this Ultralytics YOLOv8 pre-trained model on many classes, and you might see that it's detecting class 0 just for me as a person. And yeah, that's pretty easy how it is to use. And in this video, I'll demonstrate how you can easily use it, for example, with my code or them code. But with my code, you will receive this kind of flexibility where I'm creating this object, detector object, that we use to receive detections for each frame, whether it's image, video, or whatever, and you don't need to do some kind of implementations that they give for us. It's very easy, and I'll show you how you can export the same model for object detection into Onnx format and to run the inference in the same way. For example, you might see that right now it's running with 90-20 frames per second while I'm recording on the GPU, and well, it is way slower because I'm using the my webcam clone, stream clone, because I'm recording right now this video, and it's a little different. So basically, let's move on to what I did and why I did. I would like to stop this for now. Well, you might see how it works, and I'll stop it for now. Let's press Q, and it's go X. So this code is not necessary. It's only for me to disable some GPUs that I have. And you might see that from Ultralytics engine model, I'm creating importing the model that I use as a base model. That's the same as Ultralytics tell us how to use this pre-trained model. They automatically download the weights, they load these weights, and that's it. We simply need to run the predictions on it. But instead of running the predictions, I created this torch detector object. Well, basically right now I can't go into this code because for some reason my language server crashed, and I'm not sure why, so I'll go to my code. So if I go to my torch detector, I created these kind of amazing two objects, and for example, one detector that I inherit from base detector. What it has? So it has a lot of stuff as the model, input width, input hey, classes, confidence threshold, and device we want to use, and etc. By default, it is using the CUDA device, and we load this model. We define a color palette, and we run this kind of predict function by default. Well, not by default, but there is a predict function that we use to run the inference. So what we do is we simply run the inference, we pre-process image, so we receive the predictions. So then we receive these predictions, we post-process them, these predictions, and we receive the boxes, and I convert them to a detection object that is in detections. So this detection object is a very specific object, but I created this specifically for simplicity reasons. For example, when we are thinking about training our model, one thing that we need to do when we might have annotations in very different formats. So to train our model, we need to load these annotations, whatever the format have at the beginning, into these kind of detections object and load them into detections. And then I implemented this MLTU object training library so that it would be very simple to train using these kind of objects. And you might see that it's missing some kind of pre-process functions and post-process. And here comes the base detector object that I'm using here. And if I go to my base detector, it has two functions, pre-process and post-process. It's very specific to Ultralytics YOLO family, and that is implemented with Torch. But basically, it should work for all the Ultralytics YOLO family detectors. So what we do is simply we read an image, we resize it, we normalize the image, we transpose the axis as it's required, we expand the dims because it's one image, and yeah, you return the image. That's the pre-processing. And what we do in the post-processing is that from the predictions we receive these outputs, and we have the well, in Ultralytics, everything was written in a for loop, but it's way more efficient to use a NumPy. So I rewrote this to use a NumPy, and well, that's only a few milliseconds in speed increase, but that's still better to use the NumPy way than for loop. So what we do is here, we simply filter the confidences. We extract the indexes of our confidence interest. So we receive these scores that we're interested, and then we simply use the same indexes to receive the classes of our detections, and we extract the boxes from our predictions. That's also very simple. And because they come in a normalized way from a predictor, from the model, we need to, well, transform them back to the original shape to be used on our image. And then there comes the CV2 standard library to use as NMS, and I return these boxes back as we need it. And as you can see, this predict function, we simply need to re-implement this predict function. That's what I did with my Torch predictor. And this call, when we call to the model, it uses the predict. And there is a very useful wrapper that I wrote to measure the whole FPS of pre-processing, post-processing, and etc. It is there, but basically this is very useful model. Let's go to my inference model where it is. Let me see. So what is this wrapper? That it's like a decorator, but you used to use decorators as functions. But I created this as an object, and this way we can add this kind of FPS name into our object if it wasn't there, and we update this every time we call this FPS wrapper. And I noticed that it's very useful. We don't need to hard code any code into our object. If we want to use the, for example, measure FPS of the function, we simply call this as decorator, and it will appear there. So that's very useful. You can use it anywhere you want when you are trying to measure the FPS. And I added this on this detector. Okay, not here. Torch detector. Yeah, in the detector. Sorry. Yeah, I used this on the call, but if we don't want to use this, we can directly call this predict, and whatever. If you want, you can add this FPS wrapper on the predict. It's up to you. So, but I'm not interested to use it like that. So that's it about this. I'm not going too deep into the details, but let's see about this target detector a little more. So you might be interested really what is this detection object. So usually when we are using detection, we have a bounding box that might be in various types. It might be XY, XY, it might be XI, YH, with H, I mean, and etc. There might be many ways. So for simplicity reasons, that's I added box type. When we are feeding this kind of bounding box into our detections, we specify what type these bounding boxes are and whether they are relative or not. Because sometimes we have annotations that are not relative, and then we need to have image width and height. But if they are relative, we are not interested in width and height, but sometimes it's really useful to have them. So that's it. We feed the classes, labels, and etc., and we are good to go with that. If you are more interested what is this detection object, you might go to my code that is on GitHub and check this out. So basically, I'm not going to focus for it right now because later I'll be training the custom object detector with YOLO V8 from Ultralytics, and you will see how easy it is to adapt to your case. And yeah, that's it. And let's go to my another torch detector and run pre-train. As you might see, I right now was running this loaded model, and you might be interested. Okay, but if you want to kind of convert this into Onnx, it is saved here locally. You can save it anywhere. Well, when it downloads it locally, and that's it. But if you want to convert this to Onnx, I already wrote this for you. That's very simple. And I added additional functionality that is very useful when we are doing so. So what we do, usually when we are converting our model from torch into Onnx, we need to specify the input width, height for forward pass, and we specify the axis, whether they are fixed or not. And it's very useful to have like a YOLO model that has dynamic axis. This means that to this pre-trained model, we can feed smaller input size. It depends on your requirements to the model, and it will work a little faster. If you need more accuracy, we increase the input image size, and it will work slower, but it will give us more accuracy to our results. So it gives us way more flexibility. We don't need to export model into different like input sizes, and then it's very hard to know what model with what input sizes has, and etc. So that's cool. And yeah, we feed the model to send model to CPU into evaluation mode with random inputs. We send also to CPU, and we simply call this function that exports our model. And what I did is very useful is that YOLO is not Ultralytics not using this, but I saw that it's very useful that we can also save the metadata into our Onnx model. It's any metadata, and in this case, I'm saving the classes, labels, whatever you want, you can call it. I integrate this into the model. This means that we don't need a separate file to load our classes on what our model was saved. And yeah, I define the metadata, I load my Onnx model, and I save this into the Onnx model, and then I save the save model into the save name, and it already has my metadata with labels, and then I can use them. So if I go to my run pre-trained, I have already here the Onnx model I need. I uncomment these, and here my Onnx detector. And let's go to the, before running this code, let's go to my Onnx detector, where it is. Here it is. So it's very similar as before. So it has the base detector functions and Onnx inference model from MLTU package. And yeah, that's it. This handles the metadata loading. So what we feed the model path, that's okay. Input with height to our model of YOLO, we want to use confidence thresholds and classes dictionary. So as you may see, right now I'm using as none because I will load these from my model and return raw outputs as bool flag. You will see what it does. So as you may see, here is the classes, and what it does is whether if it's none or classes not given, it tries to load these kind of metadata classes, and if it's not, it will raise an error. So whether it should be saved in Onnx model or it should be given to this object, otherwise it will raise an error. And I define a color palette, this kind of random color palette to draw detections. And same as before, not the same, but very similar as before, as it was to my torch detector, I run the predictor. I receive an image, I receive the input, I pre-process this image. As you may see, I receive this pre-processed image, is normalized, transposed, and resized. I send this to my model run, and I receive the predictions. This is not a torch. Yeah, that's a mistake. It should be not a torch, but it simply extract from the predictions. Well, and then we do the same stuff. We calculate the factor of resizing factor and send this to the post process. And sometimes when we don't want to, for example, receive the detection object that I have, so for this case I have return raw output, and this will return the boxes, scores, and classes that you might use whatever way you want, or it puts everything into detection objects and it returns this detection object. And what it does, if I go, it simply, as you may see, we receive here detections from my detector, and I, for example, can apply to frame these detections. I can serialize these detections into dictionary and save this into, for example, JSON file. It's up to us. It's very, very useful, and it's very flexible to users. And that's it, yeah. And I use the same tactic, detector, FPS, and etc. So right now I'll run this Onnx model, and let's see how it runs. Detector, let's see, before it was close to 19 FPS. I haven't changed anything. Let's load it. Yeah, it loads a little slower because this is Onnx and I'm using the virtual camera. So in this case, it works exactly the same as the YOLO detector, and torch detector in case of FPS, but usually if I would be not recording or whatever, it should be faster by 20 or 30%. It's way faster. So that's it about that, and it works perfectly. As you can see, I can pick any stuff. For example, I can take my drink, but what detection here? Toothbrush? Oh, now it's bottle, not toothbrush. And that's it. As you might see, it works just fine. And now, for example, if you want, you can use my example to integrate it into your solution and to run whenever you want. Okay, one more example before I end. Let's try to use smaller input size. And let's see, before it was 80%, 9%. It should actually work exactly the same as before. And yeah, as you might see, now it comes with 47 FPS, 49, it's more than 2 times faster with smaller input size. And this is still toothbrush, not a bottle. Okay, so that's because, well, I'm doing some recordings and etc. It's not working most efficient way. So that's it, and that's pretty easy. And this is how easy to use this kind of inference. And okay, that's it for this tutorial. In the next part, I will show you how you can run the training with your custom dataset using my MLTU package. And yeah, that's it. And we'll see you in the next time. I hope this video was useful for you. If it was, smash the like button, subscribe, write any comment you want, or if you have any questions or notices, you can open issue on my GitHub channel and we'll solve it. So thank you for watching and see you next time. Bye.